Good afternoon, ladies and gentlemen. My name is Tan. So I am talking to you guys from South Korea. So I will introduce to you guys an effective dynamic slide mode control based nonlinear disturbance observer for a quadcopter UAV. The first thing I'm gonna talk to you is the problem statement. So as you know that uncertain nonlinear system control is a challenging topic in the field of control theory and application, especially in a managed aerial vehicle which is strongly affected by aerodynamics environment. Of course, there's many researches in literature to solve this issue. In the study, we have proposed an algorithm combining the nonlinear disturbance observer and robust dynamic slide mode control to deal with the problem. So you can take a look in this formula. This formula is a mathematics model of the quadcopter which summarizes. So you can take a look. Phi, theta, and besides are the attitude angle of the quadcopter UAV, and its position x, y, and z. C, phi, c, theta, and c beside are external harmonic disturbance affected to attitude dynamics. So you can take a look. U2, U3, and U4 are the controller of rho, peaks, and your dynamics respectively. So let X is a state variable vector defined by follow this formula, and then the system 1 can be rewritten as follow. This is the system 1 can be rewritten by x dot equal function of x ui plus ci, and so we can see this is a function of x and ui, and this is also the function of external disturbance. So you can take a look in this one. This is a rho subsystem or rho dynamics, and two equation here. This is the peak dynamics, and two equation here is your dynamics. So we can separately isolate rho, peaks, and your dynamics. So we have rho, peaks, and your dynamics formula. And then the problem now is to design a controller U2, U3, and U4 to ensure that the system of rho, peaks, and yaw are stable at the equilibrium point. Let us consider a second order system as follows. So why do we consider a second order system? So you can take a look in rho dynamics, peaks dynamics, and yaw dynamics. So you can take a look at the form of rho dynamics, peaks dynamics, and yaw dynamics is similar with the form of the second order system. So whereas x1, x2 are state variables, f, z are smooth function, u is a controller, and c is the external harmonic disturbance. The second part, so I will talk to you guys a controller design. First, nonlinear disturbance observer. From the second order system, you can take a look here. So we can rewritten as follow. We can rewritten by this formula where log f equal this vector, z1 equal this vector, and so on. So let us suppose that the external disturbance is considered as the harmonic disturbance formed by this formula. So where epsilon belongs to R2, and the matrix W is 2 by 2 matrix, E is row matrix 1 by 2. And here is the general block diagram of nonlinear disturbance observer. So you can take a look in this diagram. This is the exogenous disturbance model, the effect to the second order system. So via the controller U and the state variable. So this is the input to the nonlinear disturbance observer, and the output of nonlinear disturbance observer is disturbance estimate value. So we can refer to the chain study of a nonlinear disturbance observer. So we refer this research. So we have the disturbance estimation value is computed by this formula. And where is C hat is the estimate of C, and epsilon I is larger than 0, and we have the parameters of disturbance observer here, Lx and Px is computed by Px. So you can take a look here. Px is equal this vector, and Lx is equal this matrix. So epsilon I, epsilon 1, epsilon 2 is epsilon I is a positive value. So the second one, a robust dynamic sliding mode control, is designed by this procedure. So let's YD is a desired state of the system. So we have the error state. We have the error is computed by this formula, and we also computed the second term of derivative of error equal this formula, and a PID sliding surface is chosen as follow. This one is the PID sliding surface is chosen. So it can be seen that if x equal x dot equal 0, implies that the error is converts to 0. So you can take a look. If s is equal 0, it means that the error here must be converted to 0 when the constants of Kp, Ki, and Kd are appropriately selected. Let sigma is equal x dot plus lambda x. Lambda is a positive value, be a new dynamic sliding surface. It can be seen that. So we have sigma is equal this formula. So we can entirely compute to obtain this formula, and take the derivative of sigma. We have a sigma dot equal this formula. Therefore, we can withdraw to a theorem 1 less the error of estimation disturbance. Follow this formula, and assumption that this parameter is a positive value are constant. And always satisfy the following condition. So following this condition, so the sliding surface sigma asymptotically converts to 0 if a dynamics controller u dot is a dynamics controller is chosen by this equation. So from u dot, so we can find take integration to find out controller u. So we can approve by this procedure. Let's substituting the controller u. This means that we substituting u dot to sigma dot. This means that we substituting to this value u dot. So finally we can get the sigma dot is equal this formula, and the Lyapunov candidate function is chosen by v is equal 1 over 2 sigma square, and take a derivative of v is computed by this formula, and it's easy to prove that the v dot is a negative value. So it means that sigma is a dynamic sliding surface asymptotically converts to 0. So note that the controller u is computed via u dot. So you can take a look here. U is computed via U dot. So next step, we will apply the robust dynamic slide remote control and a nonlinear disturbance observer to a quadcopter UAV, a roll control. The first one is a roll control. Now we will go back to the roll dynamics mentioned in the previous section. So you guys can take a look. This is a roll dynamics, this is a roll dynamics, pitch dynamics, and yaw dynamics. Okay, this is a roll dynamics subsystem. The nonlinear disturbance observer and robust dynamic slide remote control for a roll subsystem can be obtained as follows. So the first nonlinear disturbance observer, follow this formula as we have as I have already mentioned it in the previous lesson, previous section. So this one is a robust dynamic slide remote control for roll controller. U2 dot, this is U2, we can calculate U2. And similar for pitch and yaw control, the nonlinear disturbance observer and dynamic slide remote control for the pitch and yaw subsystem of the quadcopter UAV are entirely similar to roll control. The part 3, so I'm gonna talk to you guys about the simulation and discussion. The first, the parameter of simulation. So first I'm gonna talk to you about the situation of simulation. So when t is belong to 5 to 10 seconds, the external disturbance effective to attitude subsystem is follow this formula. And when t is smaller than 5 seconds or the time is larger than 10 seconds, the external disturbance is equal 0. And this is the parameters of quadcopter UAV, and this is the controller parameter. So this is the performance of disturbance estimation in roll dynamics, disturbance estimation in pitch dynamics, and disturbance estimation in yaw dynamics. So you can take a look. The solid line, the orange solid line is the real disturbance, and the dot line, the black dot line, is the estimate value. So you can take a look. The estimate value is closely track the real value, so you can see the performance. This is a good performance. And this is control performance of roll, phi, pitch, theta, and yaw beside. So in this performance, in this simulation, we compare the performance of the proposed controller, nonlinear disturbance observer, robust dynamic slide remote control with others, modified super twisting slide remote control, non-singular terminal slide remote control, and super twisting slide remote control. So you can take a look in the black solid line. This is the proposed controller. Is the performance is better than other. The performance is always better than others. So you can take a look. This is the pitch performance. This is the yaw performance. The proposed controller is always better than others. And this is the performance of a controller. So you can take a look for the chattering phenomenon of the proposed controller is also very small and smaller than others, smaller than non-singular terminal slide remote control and smaller than super twisting slide remote control. This is a roll controller, pitch controller, and a yaw controller as well. Okay, conclusion. In this research, we introduce an effective dynamic slide remote control based on nonlinear disturbance observer for quadcopter and managed area vehicle. In the algorithm, the external disturbance are estimated by nonlinear disturbance observer following a dynamic slide remote controller combined with the estimated value is introduces to compensate for the effect of these disturbances. The strict robustness and efficiency of the proposed methods is demonstrated by the simulation result of attitude control of a quadcopter with a good tracking performance, superior stability, and no chattering effect. So this is the contribution of the paper. Thank you very much. Thank you guys for your pay attention.